This video is for lesson 11.2. So if you have not already done the Spark Your Learning about Marisol and her garden, be sure to go ahead and complete that. So notice we are looking for the border, which is the perimeter. So the outside should equal 24 meters. So go ahead and try that and then come back when you are ready to see my strategy here. So it tells me that Marisol is designing a vegetable garden, and the coordinate plane shows the area where her garden will be planted. So she can't go outside of this area, otherwise, she'll be cutting into her yard. And one grid equals 1 meter. So here's 1, 1, 1, 1. So that's 1 square meter. She has 24 meters of fencing to put around her garden. The garden can be any shape as long as she uses exactly every little bit of the fencing, so no more, no less, exactly 24 to make a border around the garden. Use the coordinate plane to show a possible design for her vegetable garden, and then name your coordinates for the corners of the garden. So I know my total has to be 24. So I think as I draw, I just want to be counting. So I'm going to start right here. You can start at a different place. I'm just going to start here and I'm going to say 1, 2, 3, 4. And I'm going to keep going a little bit. 5, 6, 7, 8. So I'm going to count. Now I'm going to go over. So I know 8. I also know I've got to have 8 to go back up. So I've got to connect these. So if I do 8 and 8, that makes 16. So how much more do I still have left? Well, 24 minus 16 is another 8. So I still have 8 left. I'm going to make a rectangle. So I want to cut the top and the bottom. So I only have 8 to share between the top and the bottom. So I'm going to cut that in half. So that is 4. So I'm going to go over 4. So I went 8, 9, 10, 11, 12. So if I go up 8, there's 20, 21, 22, 23, 24. So that's just one solution. I could flip this sideways. I could put it in a different spot, but that solution used all of my fencing. So now I'm going to name my coordinates. So remember, we always start at our origin and go over. So I'm going to go over 1, up 1, 2, 3, 4. So I have this in quadrant 1, positive, positive, 1, 4. Then I'm going to go to my next corner is 1, 2, negative 3 because I went to the left, and then up 4. So this one is in quadrant 2, so negative, positive. Down here, I have one in quadrant 3, so I've got to go over negative 3 and then down from the X 1, 2, 3, 4, negative 4. So here's quadrant 3, negative, negative. And then my last one is over 1 to the positive direction and down 1, 2, 3, 4 places. So down is a negative 4. So there are my coordinates that I chose to use. So it also asks us which of these do make 24. So I'm going to need to graph these here to be able to check this out. So I've got to go over negative 5, up positive 5, over 2, up 5. Then I'm going negative 5, negative 2, and over 2, down 2. So when I connect these, I have 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4, 5, 6, 7. Okay, so this was 6. This is 7. 1, 2, 3, 4, 5, 6, 7. This rectangle should have a top and the bottom the same. So this side here is 1, 2, 3, 4, 5, 6. So 6 plus 6 is 12. 7 and 7 is 14. So this is 26 feet. She would not be able to make that fence. So our next one here is -4. So over -4 and up 4. Over -4, down -3. So here's 1, 2, 3. So to get from here to here, there is 1, 2, 3, 4, 5, 6, 7 again. So I can see 4 here, 3 here makes 7. Now I need, so I did -4, -3, so over 1, down 3. So here's 1, 2, 3, 4, 5. And then we're going over 1, up 4. So that means this side is 7 and this side is 5. So 7 plus 7 is 14. 5 plus 5 is 10. So decide, do those add up to 24? Our next one here has -3, 1, 2, 3 to the left, and +5 up. Oops, I did not mean to put a dot there. So -3, negative, sorry. Let me start that one over. -3, +5. So here's my first one. So then I need -3, -1. So let's see, to get from here to here. So here's 5 and one more makes 6 total. And then we have over 3, 1, 2, 3, and up 5. So here's 3 and here's 3. So here's 6. And then we have over 3, down 1. And we know from here to here is 6. So it looks like all the way around we have 6, 6, 6, 6. So add those up and decide if she can use that to make a 24-meter fence. And then our last one here has over 1, up 1, over 4, up 1, over 4, up 6 is going to be right up here, over 1, up 6. So here's 1, 2, 3, 4, 5 going down. So that means there's 5 on this side and 1, 2, 3 going across. So add those all up and decide if she can use her 24 meters of fence to perfectly make a 24-meter fence using those coordinates. Okay, so when you have finished your spark, let's go ahead and head over to task 1. So before we jump into task 1, our goals for today are that we are going to be able to graph these points. We're going to call them vertices. We'll talk about that word in just a minute. So we're going to graph these vertices of a figure, be able to connect them, determine where are they, and then it will tell us we might have a missing one, and we've got to figure out where would that missing one be to make a certain shape. So it might tell us to make a triangle, and it gives us 2 points. We've got to find that third one to be able to make that triangle. So our goals for today are to get here to a 3, to graph the ones that it tells us, the coordinates it tells us, and figure out what is the missing one to make a certain shape. So that's a 3. Those are our goals. Graph and find the missing one. If you get to a 4, that means you can graph, you can find the missing one. You can also determine the perimeter of the polygon like we just practiced in our spark. So you can count around and know how much fencing or what the border is to go around. And if you can explain that and teach somebody else, that's a 4. And then a 2 is that you can graph them and figure out the shape when you're given everything. So you can't find that missing one here. So today, this part right here is finding that missing piece. And if you can name the shape given the picture, that's a 1. So let's go ahead over to task 1. So our first word we need to talk about is a vertex. Or when we have more than one, we call them vertices. So that's just the point where the two sides meet and touch together. So a polygon is a closed shape, so it has to be completely closed in. You've got to have at least 3 points. If I only have 2, I can't make a shape with that. That's just a line. If I add a third one, then I can connect them to make a triangle, a quadrilateral, a pentagon, and so on, depending on its number of sides. So the line segments only intersect at their endpoints. So I didn't draw a very great triangle right there. So they only touch right where their lines meet. So let's take a look at which of these figures are polygons and why. So it has to be closed in. The lines have to be straight. And so the only time they crisscross is where they touch. So figure 1 here has all straight lines. It's completely closed in. So I would say, yes, this is a pentagon. Straight sides, they're closed in. So this is a polygon. Over here, figure 2, I notice it has this missing piece here. So this is not a polygon. It does have these straight sides, but it's not closed. So this is not a polygon. And then figure 3, remember we need those straight lines. So this one is a oval shape. So there's no real vertices where the points are meeting. They all just continue on into each other. So these ones you can see stop here. So this has 1, 2, 3, 4, 5 vertices. It also has 1, 2, 3, 4, 5 sides. We can count the sides it has and the vertices. So I notice 5 sides, 5 vertices, where this one has 1, 2, 3 sides, but it only has 1, 2 vertices. Polygons should have the same number of sides and vertices there where they're connecting. So this one just has an infinite amount of dots all together to make that oval shape. So go ahead and complete task 1 and come back when you are ready to do task 2. So here are some examples of polygons. So we can see these are all closed in shapes. They all have straight lines. Their lines meet to make these vertices or the vertex. So I can see here 1, 2, 3, 4, 4 straight sides, 4 right angles. So this is a quadrilateral. So quadrilateral because it has 4 sides, but a better name for it because it has 4 right angles and opposite parallel sides is a rectangle. Here we have polygon, but it also has 4 sides, so I would classify it as a quadrilateral. But the sides are all equal and it has 4 right angles, so the best name for this one is a square. Here we have this triangle. So we can see 3 sides. So this is a triangle. And these 2 sides are equal to each other. So this is an isosceles triangle. And next we have 1, 2, 3, 4, 5, 6 sides. So this one is a hexagon. So a hexagon has 6 sides. This is an equilateral hexagon because all the sides are exactly the same. That means all of the angles are also the same. So here we have another example of a triangle because it has 3 sides and 3 vertices. So we've got a triangle here, and this one is a right triangle because it has 1 right angle. Next up, we have this shape here with 1, 2, 3, 4 sides. So this is a quadrilateral. But I notice the left and the right side are parallel. The top and the bottom are parallel. So this is an example of a parallelogram. Everything on it will never touch. They're just going to run by each other and never touch. It's not a rectangle because it doesn't have right angles. So this is just a parallelogram. So next we have 1, 2, 3, 4, 5 sides. So this is a pentagon. So pentagon, and it's an equilateral one because they all have the same sides. And then here's another example of a polygon. And there are an infinite number of polygons because as long as the lines are straight and it's closed in, it's a polygon. We can just draw some very random shape here. And as long as they're meeting to make these vertices in the corner and they're straight lines, this is a polygon. It doesn't have a name other than it's a polygon. It's closed in and has straight lines to make these vertices. So our last one here has one set of parallel lines. So this is a trapezoid. So sorry, that was a very terrible writing. Trapezoid is as a one straight. These two are going to cross eventually, but it is closed in with straight lines. So it's a trapezoid. It also has four sides. So it's also a quadrilateral. So those are just a few examples, just we want to keep in the back of our mind as we are looking at these different shapes today. So we can classify the polygon by the sides it has. So we've got triangles have 3, quadrilaterals have 4, pentagons have 5, hexagons have 6. We saw examples of all of those on that previous page. So here it wants us to describe the polygon with these vertices. So first we need to graph these and then decide what polygon is being made here. So we want to go over 2, up 5, over 2, up. Here's 1, 2, 3, 4, 5. So I can see it's counting by twos, but it's got a space in between, a line in between. So 1, 2, so every box is representing one unit. So here's F. So when it gives us the point, we want to make sure we label it so we can remember which one it was. So G is over 7 and up 1. So here's G. H is over positive 2, down negative 6. So here's H. And J is negative 3. So to the left, and up 1 is J. So now it asks us to connect these F to G. So I'm going to grab my line tool here and make some straighter lines. So F to G, and then G to H, H to J, and J to F. So we can see our shape here. So let's answer some questions about that polygon. So we can see that it has 4 sides, it has 4 vertices. So our first question asks us, the graph of FGHJ has how many points above X? So remember our X goes across. So how many points does it have above X? So it has 3 points. J, F, and G are above the x-axis. They're in the positive direction. And above and below x, so down below into the negatives, it has the vertex of H. So it only has one vertice that is below. So then it asks us how many points are to the left of Y. So to the left is only 1. And then, so how many are to the right of Y? So here's Y to the right, 1, 2, 3. So how many sides does this figure have? 1, 2, 3, 4. So see if you can remember what type of shape has 4 sides. Go back and rewatch part of the video if you need to. And then how many vertices does it have? So those are the points that it has. Count up those. Let's go ahead and complete task 2 and come back when you are ready to do task 3. Hey, an architect is drawing a plan for part of a bridge that makes a right triangle. That's very important to remember, a right triangle. So here is an example of one. The coordinate for two of the vertices of the right triangle are -3, so to the left, and +5 goes up. So there's A. So we want to label so we remember what is what. And B is over to down 4. So here is B. So it tells us that sides AC and AB will form the right triangle. So wherever C is, the sides are going to form right triangles. So we want to find that missing piece. Where could C be? So before we do that, what kind of angle is a right angle? A right angle is that 90-degree angle. It's going to make a perfect square in the corner. So if that's a trapezoid still, sorry. So it will make this perfect square of 90 degrees in the corner. So we want our triangle when we connect it. So we know we can see A and B here. So here's A and B, A, B. So we need to make C straight out from B, straight down from A. So let's go ahead and try that. So we want to go straight down from A, straight over from B. So let's see, where would C be located? So C is going to be over -3. It's got to be in line with A. So it's got to be -3. And then it went down to line up with B, 1, 2, 3, -4. So one location for C is -3, -4. So here's these locations we can see making that triangle there. But it also asks us, is there more than one possible location for coordinate for the vertex of C? If I look up at this picture, I can see, so yes, we've got this right triangle with the angle on the bottom left, but I can also see a right triangle here with the right angle at the top right. So see if you can figure out, so if I connect over and connect B, where is that vertex located? So there's another way we could make a right triangle using A, B. So here is another example of a different type of angle here. So we have AB is much flatter compared to this one, which was much steeper here. So A to B. So we want to decide where can C be located. So remember, we want to make that right triangle. I think I forgot a word there. So we want to make right triangle ABC. So I can connect and connect. So there's one location it could be. I could also connect here. So this is C, or this can be C. So which vertex, which point makes the right angle? So if I look here at B, it's pretty little. It's an acute angle. Here's another acute angle. It's less than 90 degrees. The right angle gets made right here. So this right angle gets made right here where A and B connect at straight points. So they make that right angle, that square can be formed in the corner here. So now we're going to draw a new right triangle, and it has to be in the fourth quadrant. So if we remember, we start positive, positive, 1, 2, 3, 4. So I want you to pause the video and go to Ed and draw any right triangle in quadrant 4. So it can only be here in quadrant 4. Draw a right triangle. So I'm going to draw one here, here, and connecting so I can see my right angle is here. So we will all have different coordinates because we all drew our triangle in a different place. But they should all have the same signs for X and Y. So which direction did we go to get to the fourth quadrant? Did we go positive or negative? Well, we went over, so we had to make X was positive, and then we had to go down, which is into the negative numbers. So Y has to be negative to get to the fourth quadrant. Over positive right, down negative. Are the right triangles that you drew all polygons? So we drew a few triangles here. So is this a polygon? It's closed in. It has vertices. So that one is a polygon. Are these polygons? Yes, they're closed in and have those straight lines. So triangles are always polygons. They have a better name, triangle. And we could even get more specific. This is a right triangle, an isosceles one, and a cute one. We can name them different things, but they are all polygons. This one is also closed in with straight lines. So this is also a polygon. So see if you can find all of the true statements about right triangles. Okay, last it asks us, how can we put 3 points on a coordinate plane and it will not make a triangle? So I'm going to try putting one in this quadrant and this quadrant and this quadrant. So if I connect these here, it made a triangle. So putting them in different quadrants isn't going to help me. So let's take a look at some of the other suggestions it gave us to try here. So, hold on, I'm loading here. We're on letter H. So, are the right triangles that we drew polygons? Oh, sorry, we're on I. So, we tried drawing them in different quadrants. That did not work. So, let's draw 1 point on one axis and the other 2 points on the other axis. So let me grab a different color here so we know. So it said put 1 on 1. So let's put 1 on the y-axis. And it said put the other 2 on the other axis. So I'll put them on the y-axis or the x-axis. So I connect, connect, connect. That still makes a triangle. So putting them on different axes doesn't help. Draw 3 points in the same angle. Draw 3 points in the same angle. So if I put them all in the same spot, that's not making 3 points. That's really just 1 point. It's all in the same place. So let's look at this last one here. Draw 3 points on the same line. So I'm going to pick this line here and I'm going to put them, let's see, let me grab a different color here. 1, 2, 3. If I connect these, there is no way for me to make these a triangle. So the only way to not make a triangle when you have 3 points is if they are all in a line. Otherwise, right, I can put them wherever and I'm going to make triangles. If they're not in a line, they're going to make a triangle. We can have really skinny triangles, really wide triangles. We can have lots of different types of triangles, but the only way to not make a triangle is to have your 3 points in a line. We could go across as well. 3 points in a line do not make a triangle. So go ahead and complete task 3 and come back when you are ready to do task 4. Task 4 tells us that an architect is designing a plan for a new building inspired by the Nycredic crystalline building in Copenhagen, Denmark. The building will have faces that are parallelograms. So I can see in this picture here that not a straight line at all. Let me use my line tool. That will look much better. So I can see that this bottom is parallel to the top of the building. I can see that the left side is parallel to the right side. So they would never touch if they continued on. And I can also see it's slanted. So it's not a rectangle, right? Lots of buildings we think about are made in a rectangular shape with right angles. But I can see these corners are not right angles. So he is making a parallelogram building. So no right angles. So because this is still a parallelogram, has all opposite sides are parallel, but this is a better name, is a rectangle with a right angle in between. So these are not right angles. So our first point is located at -5, -2. So over to the left, down to -2 is point Q. R is at 1, -2, over +1, down -2. So I can see R is here. And then S is at -2, +3 is S. So I can't just connect these. That would make a triangle. We want a parallelogram, and a parallelogram has 4 sides. So where could T be located? So let's try one thing here. Let's connect Q and R. Let's connect S and Q. We don't want to connect S and R. So I need point T somewhere over here. So let's see if we continue going straight with that line. And then I want to take this line here and I want to make it exactly the same so that they would be parallel. So I can see this one is straight across, but I recreated that same angle. And then here we are. Here's our vertice over 4, up 3. Now it wants us to see, is there a different place that we can put T? So let me erase these, and I want to keep my points there. So we have S and Q and R already plotted here. Let's see if there is a different way we can connect these. So this time I'm going to connect S and R and then R to Q. So I want to follow the same line. So Q and R is straight across. So S and T would need to be straight across. And then I have the same angle for S and R. When I connect that same angle, S and R, we can have this other point here. So I can see to get from S to R, I had to go up 1, 2, 3, 4, 5. So up 5. And then I had to go over 1, 2, 3. So I went up 5 and over 3. I need to repeat that same pattern. 1, 2, 3, 4, 5, 1, 2, 3 to find that. So instead of making this rectangle, we took it and we slanted it exactly the same, up 5, over 3. So we took it, went over 3 in the same direction for both of them. So here is another way that we could make T. So you get to choose which one you want to use as T and go ahead and draw your parallelograms. You can choose how you want to connect S, Q, and R, and then which way do you want T to go. So I'm going to do it to the right this time. So to get to S, I had to go over 1, 2, 3, and then up 1, 2, 3, 4, 5. So I want to do the same thing to R. Over 1, 2, 3, up 5, So then when I connect these, that gives me a parallelogram. Hey, go ahead and complete task 4, and then do your homework and check for understanding. If you have any other questions, be sure to let me know and we can set up a time to meet together. So remember, as you are graphing these, always go over first, then go up and down.